Hello viewers, in this video I would like to discuss Newton Raphson method, formula and its derivation and some deductions. What is the objective of Newton Raphson method? Newton Raphson method is an iterative method for finding the roots of an algebraic and transcendental equations, that is fx is equal to 0, where fx is a function of one variable x and it is same as we took in the bisection method as well as in Rebla-Falsi method. Newton-Raphson method is also known as method of tangent. To start the iterations, it needs an initial or starting value. Convergence or divergence of the method or result depends on the initial or starting value. Selection of initial value, that is x0. So 0 represents we find the interval in which function changes its sign and can take the midpoint of the interval as initial value. Now let us derive the Newton-Raphson method. Let x1 is equal to x0 plus h be the exact value or the better approximation of the root, h being a small quantity. Then fx0 plus h is equal to 0. It means x0 plus h, which is the exact or better approximation, will satisfy the equation. So once we put x0 plus h in the equation, it should be equal to 0. Expanding fx0 plus h by Taylor's theorem, we can have fx0 plus h is equal to fx0 plus hf dash x0 plus h square upon factorial to f double dash x0 and so on is equal to 0. Neglecting higher order terms, we get first two terms of right hand side, and these are fx0 plus hf dash x0 is equal to 0. From here we can find out value of h, which becomes h is equal to minus fx0 upon f dash x0, provided f dash x0 is not equal to 0. Now we substitute this value of h in x1 is equal to x0 plus h, and we get this expression, that is x0 minus fx0 upon f dash x0. This is the next better approximation. So x1 is the next better approximation of the root of the equation fx is equal to 0, then x0. Since x1 is not an exact root of the equation fx is equal to 0, therefore we perform another iteration to find the next better root. To get x2, the value of x0 is replaced by x1 in the formula. Therefore, x2 becomes x1 plus h, which is equal to x1 minus fx1 upon f dash x1. And n plus 1th iteration also we can write down, and that becomes, so this is xn plus 1 is equal to xn plus h, which is equal to xn minus fxn upon f dash xn. So these values have been calculated on nth root, and we are calculating n plus 1th root, and takes values 0, 1, 2 and so on. We will terminate the iterations when the absolute value of the difference between two consecutive approximate roots is less than or equal to error tolerance, that is xn plus 1 minus xn mod is less than equal to epsilon. This may be prescribed wherever we are applying Newton-Raphson method or requirement according to the situation, and this mod xn plus 1 minus xn should be less than equal to epsilon, where epsilon is the error tolerance. Error is a pre-assigned value, very small positive number based on desired accuracy. Now there are a few deductions also of Newton-Raphson formula. So we see what are those deductions. So there are four deduction formulas here, for 1 upon n, for under root n, 1 upon under root n, kth root of n, and these are in general form. So xn plus 1 is equal to xn 2 minus nxn. This is for 1 upon n. For under root n, this is the formula. For 1 upon root n, this is the formula, and for kth root of n, this is the formula. So these are the formulas which are the deductions from Newton-Raphson method. Thank you. Hello viewers, in this video I would like to discuss example third of Newton-Raphson method. Example is, derive the formula xn plus 1 is equal to 1 by 2 xn plus a upon xn, where n takes 0, 1, 2, 3 and so on values, for finding the square root of the positive number a. Use it to find under root of 12 correct to 4d. Actually this is the deductions of Newton-Raphson formula, and in the derivation and formula video I have given this formula, and here we are deriving it, and we will calculate square root of 12. So let's say x is equal to under root a, x square minus a is equal to 0. We have squared both the sides. Now we say fx is equal to x square minus a, then we find out derivative of this, which is 2x. Now we apply Newton-Raphson formula and see, this is the nth general formula of Newton-Raphson, and we substitute values of fxn and f dash xn in this formula, and we simplify and we get the formula, which is xn plus 1 is equal to 1 by 2 xn plus a upon xn. This is the deduction from the Newton-Raphson formula. And now we will calculate under root 12. A is equal to 12, so x square minus 12 is equal to fx, and we see when we put value of x as 3, the function value comes negative, and when we put x is equal to 4, function value comes positive. So it means root lies between 3 and 4. Now we take initial approximation or initial root as 3.1, and we apply the Newton-Raphson formula to get the next approximated root, that is x1, and it comes 3.4855. We apply again and calculate x2. It is 3.4642, and third 3.4641. These two are x2 and x3 are correct up to 3 decimal places. We calculate next, which comes 3.4641. So we got the root correct up to 4 decimal places, and we stop here. Thank you. Hello viewers, in this video I would like to discuss about geometrical interpretation of Newton-Raphson method. Here we see there is a curve y is equal to fx, and it cuts x-axis at certain point. We start with an initial approximation, that is x0, and we see that value of function at x0 is fx0. We draw a perpendicular from x0 to the curve, and at the intersecting point we draw a tangent which cuts the x-axis at x1. This tangent makes an angle theta with x-axis. Again we take x1 as a point, and which is the next approximated root, and from here we draw a perpendicular to the curve. At the intersecting point we draw a tangent, and it cuts x-axis at x2. From here again we draw a perpendicular to the curve, and from this intersecting point we take tangent which cuts at x3, and we keep on moving till we reach to the root, or which is very near to the root. So we can say that Newton-Raphson method is based on linear approximation of the function using a tangent to the curve. Starting from a single estimate x0 that is not far from the root, we move along the tangent to its intersection with the x-axis and take that as an next approximation. This is continued until either the successive x values are sufficiently close or the value of the function is sufficiently near 0. Now we can write down that tan theta is equal to fx0 upon x0 minus x1. We take this rightmost triangle and we write down the value of tan theta, which is of course is equal to derivative of the function, that is f dash x0. From these last two values we can write down x1 is equal to x0 minus fx0 upon f dash x0. This is the formula of Newton Raphson method, and we can write down it in general form also. Let's take example based on it. It's example 4 of Newton Raphson method. Find the real root of equation x minus e to the power minus 2x is equal to 0 using the Newton Raphson method. We see that here if we put x is equal to e to the power minus 2x, we have two curves here, y is equal to x, which we have drawn here, and y is equal to e to the power minus 2x. So we get the intersecting point of these two curves, y is equal to x and y is equal to e to the power minus 2x. That will be the root of the equation. It means the value of x at this intersecting point satisfies the equation. So we say fx is equal to x minus e to the power minus 2x. We find out its derivative, f dash x is equal to 1 plus 2 e to the power minus 2x. Now we put this value, these two values in the formula. This is the general formula of Newton Raphson method, that is xn minus fxn upon f dash xn, and takes values 0, 1, 2 and so on. Now we put value of function and its derivative in the formula. N is equal to 0 we take, so we will find out x1, but the term which is xn minus e to the power minus 2 xn upon 1 plus 2 e to the power minus 2 xn, we first calculate this one, and we take x0 as 0.5. So we take x0 as 0.5 as an initial approximation, and this term we write with minus sign, which is h0 we can denote. Calculate this term, which comes this. So our root will be x1 will be 0.5 minus h0. So x1 is 0.5 minus h0 is this value, and this comes 0.42388. If we say in other words, it is x1 is equal to x0 plus h0. h0 is with negative sign, therefore we can say x0 minus h0. Now we have this general formula and we keep on continuing next approximate roots, and these are the roots here, first, second, third iteration after we got this. Now these are the error values. It means we can solve the equation with exact values also, and we see there is no error in third iteration, and we got the exact root, and the exact root is 0.426300275. Thank you. So viewers, in this video I would like to discuss two examples of Newton Raphson method, example 1 and 2. The example is, using Newton Raphson method, find a root of the equation x square minus sin x minus 2 is equal to 0. Correct up to 5 decimal places. Fx is x square minus sin x minus 2, which is equal to 0. Now let's use the concept of bisection method and find an interval in which root lies. We take random values of x and put in the function. So let's take x is equal to 1 and see that it is function value is negative here. We take x is equal to 2 and function value is positive here. It means we found one interval 1, 2 in which root lies. Now let's take midpoint of the interval, which is 1.5 as x0, that is initial point or initial approximation of the root, and we use the nth iteration Newton Raphson formula, which is xn plus 1 is equal to xn minus fxn upon f dash xn. We substitute values on right hand side, and so we see xn minus, here we put fxn, it means function value at xn. So xn square minus sin xn minus 2 upon derivative of function. Derivative is 2x minus cos x. So we put 2xn minus cos xn. Now we simplify it with the help of 1.2 because n is 0 and n plus 1 becomes 1. So x1 is equal to x0 minus x0 square minus sin x0 minus 2 upon 2x0 minus cos x0. We take x0 1.5 and substitute in this value or expression. So we get after calculation x1 as 1.75511819. Now we will go for second iteration, that is n is equal to 1 and we will obtain x2, that is next better approximation of the root. So same as x3, both of them are same up to 7 decimal places. Now we go to next example. In this example, we have to find a root of the equation 5x minus cos x minus 1 is equal to 0, correct up to 5 decimal places. Here fx is equal to 5x minus cos x minus 1 is equal to 0, and we find out one interval by putting x is equal to 0 and 1, and we see function value is negative and positive here. So in between we take any value between 0 and 1, mid value 0.5 or 0.4 or 0.6. So we can take any value as an initial point. Here we take x0 as 0.3 as initial guess of the root, and we see that Newton Raphson method's nth formula is xn plus 1 is equal to xn minus fxn upon f dash xn. Now we substitute n is equal to 0 and get this value by putting the xn, fxn and f dash xn here. The denominator is derivative of the function. Now we put x0 in this as 0.3 and calculate value of x1. So by putting x0 as 0.3 in this, we get value of x1 as 0.3859852. This is the first root or next better approximation of the root. Now we calculate x2 by using x1 and see the value of x2 comes 0.385335. Now we calculate x3 by using x2 and see that both of them, x2 and x3, are same up to 7 decimal places. In the question it was given that calculate the root up to 5 decimal places, correct up to 5 decimal places. So here we got up to 7 decimal places. Our objective has been obtained and this is the root value. Thank you. Hello viewers, in this video I would like to discuss two examples where we will calculate imaginary roots of the function, and these examples are 5th and 6th of Newton Raphson method. Here in the example we have to find out complex root of the equation z square plus 2z plus 2 is equal to 0. Initial guess value of the root may be taken as I. Here fz is given and x0, or here we can say z0 because it is a complex root. So z0, which may be in the form of x plus iy form, we may take. So we can write down z0 is equal to 0 plus 1i, which can be written as 0.0 plus 1.0 into I, or in bracket form 0.0 comma 1. So if this is the initial guess which is given to us, and we have fz which is z square plus 2z plus 2, we can find out its derivative which is 2z plus 2. We substitute this in Newton Raphson formula, and instead of x we have used z here for writing the formula. So zn plus 1 is equal to zn minus fzn upon f dash zn. We substitute value n as 0 and we find out z1 is this. In this we substitute values of z0 and simplify this expression. Once we simplify, we get this says minus 3i plus 3 upon minus 4, which is minus 0.75 plus 0.75i. So this is the next approximated root. Next approximation in similar way, and can write it into tabular form where real part and imaginary parts have been summarized here. So these are the real, and this is the first iteration. Z1 value, Z2, Z3, Z4, Z5 have been given, and in the last fifth iteration you can see there is no error because we can find out root of this equation with the help of calculator also, which is an exact root. So we see there is no difference between the approximated and exact root. So root is minus 1 plus 1i, and it is correct up to 6 decimal places. This result has been checked with the help of MATLAB programming also. Thank you.